My name is Amit Prasid, and the topic that I'll be discussing today is depth first search. Depth first search, or DFS, is a graph traversal algorithm that can be used to search for a node in a graph. As the name suggests, DFS explores one path in the graph completely until it can no longer find any nodes to explore. Once this happens, the algorithm backtracks and starts to explore the immediately previous unexplored path. It continues in this manner until it can no longer find any nodes to explore. There are certain notations associated with the DFS algorithm. Every node in the graph is assigned a color which changes as the algorithm progresses. If a node is white, it means that the node has not yet been visited by the algorithm. If a node is gray, it means that the node has been visited, but all of its branches have not yet been visited. If a node is black, it means that a node, as well as all of its branches, have been explored completely. Every node also has two associated time values, the discovery time D, which is the time at which the node becomes gray, and the finishing time F, which is the time at which the node becomes black. The DFS algorithm also keeps track of the predecessor of every node that it visits, and this is used to construct a DFS tree or forest at the end of the algorithm. The DFS algorithm has an initialization phase in which every vertex U in the graph G is colored white and its predecessor is set to nil. A global time counter is initialized to 0. Once this is done, the algorithm proceeds to visit every white vertex U in the graph G by calling a DFS visit function to the node U. The DFS visit function on node U does the following. It colors the node U gray, indicating that the node has been visited. It then updates the discovery time of the node U to the value of the current time counter. And then, for every white vertex V that is adjacent to the node U, it performs two functions. First, it updates the DFS tree to indicate that the predecessor of V is U, and then it calls the DFS visit function recursively on the node V. Once all the adjacent white nodes of U have been processed, the processing of U can terminate. The color of U is set to black, and its finishing time is set to the value of the current time counter. Now let's take an example. Let's assume that our algorithm starts processing the graph from node 1. The node is colored gray, and its discovery time is updated in the first box which is next to the node. Node 1 has two neighbors, 2 and 3. Let's assume that our algorithm picks node 3 for processing first. Node 3 is colored gray, its discovery time is updated as 2, and the DFS tree is updated to indicate that the predecessor of 3 is 1. In the same way, the algorithm discovers node 5 and 4. Since 4 does not have any white neighboring nodes that can be explored, its processing terminates immediately. It gets a finishing time of 5, is colored black, and the algorithm backtracks to node 5. In the same way, the processing of node 5 also terminates, and the algorithm backtracks to 3. Node 3 has a white neighbor that can be explored, which is node 2. So the algorithm proceeds to node 2. It gets a discovery time of 7, but there are no white neighbors that can be explored from node 2. So its processing also terminates with a finishing time of 8. And the algorithm backtracks to node 3 and finally to node 1. The DFS algorithm terminates at node 1 with a finishing time of 10. The predecessor information that has been recorded during the DFS algorithm can be used to construct a DFS tree, which indicates all the vertices that are reachable from the starting vertex. But it is worth noting that the DFS algorithm need not always form a single tree for a given graph. For example, in this graph, the nodes 2 and 6 are not reachable from node 1, and the node 1, 3, 4, and 5 are not reachable from the node 6. In this case, the DFS algorithm needs to be run multiple times using different starting vertices so that all the nodes can be covered, which is exactly what the algorithm does. In this case, there will be multiple DFS trees formed, or the collection of all these trees, or a DFS forest, is formed. It is easy to evaluate the complexity of the DFS algorithm. Every node is explored exactly once, which gives us a complexity of theta of V. For every node U, all the edges starting from U are explored. When we do a summation over the entire graph, this gives us all the edges in the graph. So The complexity of DFS can be summed up to be theta of V plus E, where V is the number of vertices in the graph and E is the number of edges in the graph.